This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay. So, right. So I'm going to just quickly finish off where we were last lecture. We didn't finish all of sensors and we didn't even talk about actuators. Guys, we're not going to talk much about actuators in this subject. You'll see it's a can of worms that requires an entire subject in itself, really. Okay, so I gave a list of inherent issues with sensors. So going back a couple of slides, here. So calibration, nonlinearity, sampling, noise, and failures, and how to deal with some of those things. So I have aliasing as one of the issues. Up the top there is a sinusoid. So it's a high-frequency sinusoid. It's 9 kilohertz, that sinusoid, and it's sampled at 8 kilohertz. Okay, so immediately you should have some warning bells. If you've done any signal processing, Nyquist sampling theorem, all that sort of stuff should be going off your head. 9 kilohertz, we're sampling at 8, and the samples of those big black dots there, it actually, if you reconstruct it, it looks like a 1 kilohertz signal. Okay, so if we have high frequency components present in our sensor, raw values that are coming in, it may look like something else in terms of the values that we read. And that's called aliasing. So how do we get rid of aliasing? It's pretty simple. You just whack a low-pass filter on your input to get rid of any high-frequency content. Okay, that's typically the first thing we do with sensors. Whack a low-pass filter, get rid of any things like vibrations or high-frequency noise. Digital oversampling is also a way of getting around that. Once again, it's not a digital signal processing course, so you can Google digital oversampling and see how that works in order to reduce aliasing. A couple of pictures up here in terms of image processing, what happens when you have aliasing. Imagery is really just a digital sample of something. Okay, if you think pixels being a digital representation of light intensity or colour or whatever it is, you get basically optical blurring out of aliasing. So there's a couple of pictures there. Once again, you can go and look that stuff up if you're interested. And surely in signal processing or advanced signal processing, you'll probably look at such things there. One thing that's often overlooked, so we've dealt with noise, we might have dealt with calibration, bias and sensitivity, but faults are another big thing. Now for little designs like designing a little robot vacuum cleaner that can get around an obstacle course or some toy or something, maybe a fault doesn't matter. Maybe you engineer a fault in the sensors so someone has to go and buy a new version of the toy. But for mission critical stuff, life critical stuff, it's actually a very difficult problem. What do you do with faults in sensors? So typically what you do is use redundancy. Okay, so if we have multiple values of the versions of the same sensor, then if something goes wrong, then perhaps we could ignore some of the sensor data. That's a tricky question. Which ones do you ignore? What's the algorithm for ignoring it? How many would you have? How many do you need to ensure redundancy? And I'll give you a nice example because it involves an Australian aeroplane. Now, Qantas have an impeccable safety record. So, no big crashes or anything like that, touch wood. But there was a major incident just over 10 years ago. And from the outside, if you looked at it, the plane started pitching violently. totally without warning. And any unrestrained passengers, people that undo their seatbelts and just sit there, basically got slammed into the bulkhead or the overhead storage lockers or whatever. So 12 serious injuries. Now, how did it happen? Well, it's a cyber-physical system. It's an embedded system, there's embedded processing in there and all that. There are 3 sensors on the nose to measure the angle of attack. What's the angle of attack? It's essentially, right, the relative angle of the plane in order to know if you're climbing or you're sinking. Okay, so it's got 3 AOA sensors, and they're so important it actually has 3 of them because if one of those goes down, you're in big trouble, right? The aircraft could stall, and you don't want to stall a jetliner. And because you've got 3, right, you normally pick an odd number of sensors so you can have a voting decision, and there's always an odd one out, if you like. And we've got a nose, there has to be 2 on one side and 1 on the other. It doesn't divide very nicely. So you've got number 1 on the left and number 2 and 3 on the right. So these sensors have to deal with all sorts of weird stuff going on, low temperature obviously and things like that, but different positions, gusts, spikes, failures. So they have to be pretty well engineered, and there's a lot of problems that have happened with sensors on aircraft, particularly airspeed indicators, icing over and all that sort of stuff, and disastrous effects. So what happened here? So those sensors, the angle of attack, they're only sampled at 20 hertz, 20 times a second. It's not very fast, but think about it. The angle of attack of a jetliner is not going to be violently changing anytime soon. So 20 hertz is sufficient in order to get enough data. And the idea is you compare you sample each sensor and you compare them to the median of the 3. Now, if the difference is larger than some threshold, so it's some predefined threshold, for more than 1 second, what happens is the sensor's flagged as faulty, and it is essentially, it's ignored for the rest of the flight. Now, this sort of reasoning assumes that it's unlikely to get multiple failures all in the one go, right? If one does die, it's probably only if something does die, it's only probably going to be 1. Then, if you assume that all 3 sensors are functioning okay, what happens is you just take the mean of numbers 1 and 2 because they're on different sides of the aircraft. So just to sort of, get a nice balance of both sides of the aircraft. Okay. Then if you have a difference between numbers 1 and 2, and the median is larger than some threshold, smaller threshold, you use the previous average value for 1.2 seconds. Okay, so this is all built into the A330's processing of the sensor data. So what happened? So there were 2 spikes in the number 1 sensor, and they just happened to kind of get around some of these fault tolerance conditions. So the first fault was shorter than 1 second. So you imagine it's reading some static value and then it has a spike of some sort. It could be a positive or negative spike. And it was shorter than 1 second. So that third point there didn't hold. It didn't ignore that sensor value because the spike was too short, basically thinking, oh, it's just a momentary thing. And a second spike came along 1.2 seconds after the detection of the first. And so essentially what happened was it just accepted that bad sensor data, right, in terms of the average, because it's taking the average of 1 and 2 here. And such a simple thing happening, the result was immediately, because it was on autopilot, the aircraft just pitched nose down 8.5 degrees. Now, for those of you with any flight experience or anything like that, 8.5 degrees is significant, and if it's an immediate pitch down, it's bad, right? It doesn't sound like much, but the result is people, fly up and hit the roof. Okay, so that's a nice little example showing you that even redundancy doesn't protect you against bad things from happening, right? The algorithm has to be engineered such that you think you can cover all possibilities of what may happen. All right, so sensors are messy, but we have to deal with them. And as I said, they're all the issues that we have with them. On the actuator side of things, most actuators are as I said before, motors, really. Whenever I think of an actuator, I think of it something spinning, something moving on a gear base or something like that. To give you an idea about the difficulty of dealing with motors, motors are terrible to deal with. They are slow, bulky, inductive, they heat up, they spike things, massive voltage spikes, and they need a lot of current to drive them. So, for instance, a little hand like this, you have to have control over a motor such that you can pick up something very small, like a coin, something perhaps soft like a plastic cup or a paper cup. If you squish it too hard, right, you've got to limit the motor torque, otherwise you're just going to crush the cup. Or if you wanted to pick up a ball, perhaps, or something slippery, you need to apply a bit more force to it, as long as it's rigid, right, you don't crush it. So a device like this obviously has inputs as the sensors and nerve impulses, right, from the upper arm or further up the arm. And also there could exist pressure sensors in the fingers and joints and things themselves here. But as I said, it's a very difficult problem. How do you control such motors in here? I'm going to show you how they're controlled. Motors, as I said, they require a lot of current. Even small ones like that require reasonable levels of current. Typically current that a microcontroller cannot deliver. Microcontrollers, these fragile little things, they can only give you a few milliamps. If you're lucky, maybe microamps. So the problem is, how do you actually get current to a motor in order to make it do something? And the trick, basically, is to use what we... I love how it's now... It used to be almost a slang expression, but now it's an accepted expression, bang-bang control. What the heck does bang-bang control mean? Bang-bang control is like a really simple way of off-on controlling something. So if you've done control systems before and you've done fancy PID controllers and all that sort of stuff, this is the caveman's version of controller. It's either on or off, on or off. Now, let's look at that top graph there. We want to spin up a motor, let's say, a rotational motor up to a certain angular velocity, like in that picture there over a certain time. If you applied a current to do that, you would need a significant current. You need a current amplifier to do it. It's quite messy to control something like that. But bang-bang control allows you, down the bottom here, to give rapid pulses, pulse width modulation essentially, to the motor and rely on the fact that motors have a bit of inertia to them. Okay? So if you look at the middle graph now, that's a zoomed in part of the RPM, or the angular velocity, of the motor. And by pulsing the motor, you are essentially giving it little steps up, and then it steps down a little bit as the RPM drops off due to friction. And instead of having to have a continuous current going into this motor in order to spin it, you can just pulse it. And this pulse here is only a 10% duty cycle pulse. So you're only really switching on for 10% of the time and off for 90% of the time. So obviously it's a slightly slower response because you get that fading of the RPM signal in the middle there, but overall, if you zoom right out, it looks like this beautiful sort of slow first order curve where it gets to its required angular velocity. Okay, so we use PWM to drive the motors. Indeed, that's how the motors on the Kabuki robot are driven, by PWM, okay, because it's much more efficient and it requires simpler circuitry. It's easier to build a switch that switches large currents on and off than it is to build an amplifier that can handle large currents but also fine-tune them. It's very difficult to build amplifiers like that. It's easier just to build a bang-bang controller like that. And the mechanical model of a motor, just to give you a bit of an idea of the difficulty of the physics of all this, is down the bottom here, if you've done mechanics, maybe you're familiar with this. But this is Newton's law for rotation, basically. So instead of F equals ma, we have F equals I dw dt, or omega dt, where that's the angular velocity, not the linear velocity or translational velocity. And it's actually proportional, so like F equals ma is proportional to current. Currents are what drive motors. And they're related by this torque constant. Generally speaking, the higher the torque constant, the better the motor is, if you like, because it gives a stronger relationship between the current you put in and the force that comes out of it. There's two other terms on there that are subtractive terms from the force. There's friction, so that scales with the rotational velocity. Kind of makes sense. The faster it goes, the more friction it gets. And then there's a load torque. So if you've got something hooked onto the end of the motor that's sucking torque out of the system, if you like, then it's a net negative effect. But a motor, if you take a motor and you put a current into it, obviously it spins. If you do the opposite and you spin the motor, you get an induced voltage, right? And then the current out of that. So motors and generators are sort of synonymous. They're essentially the same thing. And interestingly, up the top is the electrical model of an actuator, a motor. And it says the voltage across it is equal to Ri plus L di dt. Now, for those of you who remember your circuit stuff, that is modelling the motor as an RL circuit, basically. It's got inductance, and motors have a lot of inductance. There's coils inside them. Coiled wire means inductance. And it has a bit of linear resistance as well. So it's a first-order model in terms of the current there. But more interestingly, that last term is a term that generates a back EMF. So in other words, the faster the thing goes, right, you're powering the motor, right? So you're powering it up with the current, with the voltage, but it's also generating voltage as well. So in the stators or the windings of the motor, right, it's also resisting you, if you like. Resisting is probably a bad word, but because it's acting as a generator at the same time as a motor. So you've got that term there. And this is why motors are really difficult to deal with, because you have these different effects here. They are so difficult, in fact, that we typically empirically model the motors. We get known operating points for them and work off that, rather than try and work off these DE models exactly. Okay, so actuators are terribly messy things. We're not going to go into too much detail about how to drive motors and such like that, because, as I said, it's a complex area that involves physics and all that sort of stuff as well. All right, so now you've got a taste of how complex things can be. I want to talk a bit about embedded processes. So the link between the cyber and the physical part of a system. So I'm going to talk about microcontrollers, very special class of processors, and DSPs. DSPs are, we can just skip DSPs because we're not doing signal processing in this class, although some of you had signal processing before this class. So maybe you can see the applied side of it. So Chapter 8 is our reference. All right, there is one big monster in the market of general purpose computing. So when I say general purpose, PC, laptop, whatever, you know, stuff where people hack around on. And that is Intel. And in particular, it's the x86 architecture. Okay? So that means basically that if you are in whatever flavour of chip is built in order to be a CPU of a computer, it essentially has to support the Intel 86 architecture. Why? Because it's just the big boss around, right? Everything supports that. Years ago, Apple had a PowerPC architecture as their CPUs many years ago, but they switched to Intel because they just realised it was too hard trying to fight their own game with their own processors, with their own instruction sets and all that sort of stuff. So that's dominant. Now, luckily, because you're doing this subject, embedded systems, there's no dominance. There's actually quite a big field of processors with their own instruction set architectures. Okay, so it's not just about different silicon with the same instructions you can run on them. It's different silicon with different architectures. It makes it much more interesting. Now, you can understand embedded processors have a really dedicated function. For instance, control a car engine. This is not for some hacker to get in there and write a bit of C code or something to do something fun or write a game or something like that. This is do a specific task and do it well and do it in a reliable, repeatable way. So if you make them specialised, it obviously gives you some extra benefits, less energy because you don't have to do everything or be able to do everything. You just restrict yourself to a very small amount of operations. And you can then have specialised hardware in there as well. Okay, so embedded systems are actually much more fun than these general purpose computing systems because you can really get down to a good level of optimization and reliability. Now, if you've done signal processing before and you've seen FIR filters, finite impulse response filters, they are an example of processors. They are very specific processors. They involve specific numerical tasks and have functional units that do that. So, for instance, if you're implementing a little FIR filter with delays and coefficients or taps of particular delays, that's what the inside of it would look like. Very particular units, and you could program the taps in there, for instance. Those coefficients A, in this case, are all a quarter. So it's highly specialised and implements canonical signal processing algorithms. We won't talk about DSPs because, once again, they're a world unto themselves. But they're a family of processors. Well, we're going to focus on our microcontrollers because these are what you're going to be programming, and these are ubiquitous everywhere. What's a microcontroller? So sometimes it's written as UC, micro C, whatever, but it's a single integrated circuit that pretty much has everything on it. So you have memory on there, onboard memory on the chip, I/O stuff on there, so things like serial ports, what other things? Just digital I/O, that stuff, maybe even analog ports if you want, and timers and all that sort of stuff. So it's an all-in-one. And you can see up there already, there's a big family, and they come in very different forms and sizes. ARMs, Arduinos, PICs, Atmels, all that sort of stuff. Okay, so it's a fun sort of, what do you say, subculture or something of processors, microcontrollers here. Right, they also have special things like sleep modes and stuff like that, which makes them even more fun to operate because you can get right down into low-level programming and configuration for particular setups. I'm going to show you an example of what you are going to do play with in the workshops. And I'll find my pen. Where the heck is my pen? Here. So this is the microcontroller that is in the myRIO board that you guys will program your Kabuki with. It's actually really cool. I love this processor. It's a Xilinx, how do you say that? Zinc? Zinc 7010. And it has two processors inside it. Let's, I'm going to just get rid of these bits here, just because that's a little confusing. What does it have? It has a processor on the top that is a full processor in the normal sense. It's an ARM9 processor, I think, with an ARM7 instruction set. Is that right? Yeah, it's a Cortex A9. And what that does is that runs an operating system. That's got a full-blown little operating system on there. So it's quite a, quite an advanced processor. It can, it has, OS. It's got Linux on there basically, and it has real-time operating extensions and stuff on there. Down the bottom here is an Artix 7 FPGA. So there are two components to this. You can program the Cortex A9 in order to do, program it in C, right, to do stuff. And down the bottom, you've got a configurable FPGA that handles a lot of the low-level I/O stuff. There is also, obviously, it's very small here, but there's a bridge between the two, so they can talk to each other. So you've got this high-level processor that has operating system on it, and a very low-level, dedicated, task-based FPGA that's hardware-based. That's also reconfigurable. You'll be programming this with what's called a fixed personality. So it's already got all of the required logic to deal with serial ports, analog and digital inputs, audio, accelerometer, all that sort of stuff. You guys will be primarily focused on programming this and reading the sensor data through this here. Okay, so it's a really, as I said, a really cool architecture. You've got two in one, an FPGA and a more standard microcontroller. So what's the basic architecture of a microcontroller? So that Cortex A9 there has a separate control and data path. So a control unit and a data path unit. And this is very common with single-purpose processors. Okay, so a single-purpose processor might be something that does a very specific task that you never, ever program again. For instance, a dishwasher controller. That doesn't have a port on there for me to go and get my laptop and start changing the program on there, right? It's burnt in there forever. It will do its thing forever. So it's very similar. It has a data path and a control unit. But in a normal programmable microcontroller, you have a general data path, but more importantly, the control unit doesn't store the algorithm itself. The algorithm is stored in the memory, and it's accessible via the instruction register, IR there. Okay, we can also pull stuff out of memory as well to store it into registers in order to do calculations and such like that. Okay, so let's have a bit more of a detailed look at what a microcontroller really does. So the control unit has a sequence of desired operations stored in memory. It's like got its own dictionary, if you like, where it knows exactly what to twiddle based on a particular instruction. And what's it twiddling? Well, it's twiddling control of the ALU, the arithmetic logic unit, control of the registers, sending stuff out to memory. So it's like, it's got, as I said, like a lookup table of, if it sees that instruction, I know to do these various things. But what is an instruction? Instruction's broken into several sub-operations. Well, before you actually run an instruction, you have to go and get it. And the micro here goes and fetches the next instruction into the instruction register, IR. So here's a piece of memory, and you'll notice that these are memory locations here. They could be in hex, whatever. You see that there's programs stored in there. This is assembler, pseudo-assembler, and over here is actual data. The memory is just, it's shared. There's instructions in one subspace of the memory, and then there's also data that's used as well. And what this micro does is it goes and uses the program counter to go and fetch the next instruction. For instance, load. There's a load instruction. Go and load into register R0, the memory location, the value at memory location 500, which is 10. So it would store that in there. But it firstly has to load it into a register to store it, pull it out of the memory and hold it there. Then it has to decode it, work out what to do with it. then it actually has to go and fetch what it needs. Now, for instance, that load operation there, once it's worked out that it's a load operation, it has to then go and grab the register values, R0 in this case, and a direct memory access as well. Then it actually does the execution. So it pushes it through the ALU, right? Maybe it's doing some math operation, or maybe it's just pushing it through the ALU to get back into the registers. Finally, it can then store the result either in registers or in memory, or from register to memory, or whatever. But we notice that there are distinct elements, sequences in the instruction cycle. We're fetching, decoding, getting the arguments or the operands, executing it, and then saving the result. So how can we speed up the process, right? Is there a way we can speed up the process? We seem to be doing some things in order, and yes, we can. Who's heard of pipelining before? Okay, great. Pipelining is fantastic. Here's the analogy of pipelining. Let's say myself and someone else are washing and drying dishes. It's a two-step operation. Okay, so before this is a 5-step operation, 2-step operation. And we've got, how many dishes have we got to do? 8. So the non-pipeline version is I sit down and do nothing. I'm going to dry. I sit down and do nothing and wait for the person to wash 8 dishes, and then I go and dry 8 dishes in a row. The pipeline version is you do them as they come, right? You start up a chain operation, if you like, that 1 is being washed. I'm idle for the first bit. But then as soon as 1 is washed, I'm drying 1 while 2 is being washed, and they're being passed across. Okay? It's overlapping. And that's okay, because the person who's doing the washing is a separate functional unit. They can wash separately from me drying. That's how it works. It's very simple. So in my little stages of execution here, over time, I can be fetching, so I've gone and fetch instruction 1. And as I move across in time, so the second column across here, I can be decoding that instruction while I'm fetching the next one. Right? Because they're independent, well, we'll see, sort of independent operations, aren't they, right? And we move along over time, and we can stack up the pipeline so that at any one slice in time, so maybe this slice of time here, we're sort of doing multiple things at once. We are storing 3, we're executing 4, we're still getting the operands for 5, and we're decoding 6, and we are fetching 7. So we've filled up the pipeline. And this has obvious implications in speed. Look at the non-pipeline dishwashing algorithm versus the pipelined one, right? Okay, so pipelining increases the instruction throughput of any processor, but in particular microcontrollers. Now, most modern processors are pipelines, so something we have to deal with. If you want a more detailed picture, this is a little 32-bit machine, and it's pipeline. So this is a particular type of architecture. It's tried to be kept simple. It's in the textbook here. It's 32-bit machine. What does a 32-bit machine mean? It means that the instructions are 32 bits wide. Okay, so you've got bit 31 down to bit 0. That's how wide your instructions are. Every instruction is 32 bits wide. And that means that the program counter, which points to the next instruction, increases by 4 bytes at a time. We normally store things in bytes, so the 32 bits is 4 bytes, 8 by 4, and then every instruction that executes, the program counter skips ahead 32 bits, or 4 bytes, ahead, to grab the next instruction. So the important thing is that in between the stages, we have these latches to almost separate each stage so that we can't have something propagate through when we're not ready to the next stage. And that facilitates pipelining, those latches there. So on each clock edge, basically the latch data gets clocked across as we go. Now, That's great. But there's a problem. This system would be okay if there were no feedback. But any reasonable machine, processor, has to have feedback. Okay? So conditional branching is a form of feedback, right? Think of it in C at a bit of a high level. If something, do something, else do something else. That is a conditional branch that will change the program counter dependent on a calculation or comparison. So it means that basically there's a way of feeding back in a program counter, a new program counter. There's also the mechanism in order to write the value, the output value, back into the register bank. And so this can cause problems. If there's feedback from previous operations coming back into some of the middle functional units, we've got problems. So what are the functional units here? We've got the ALU. That's a functional unit. We've got the instruction memory, register bank. Sorry, ALU's here. What am I doing? That's an add operation. And data memory. So these functional units are going to be the key things we can't overload, if you like. So how does pipelining work? Well, to stop hazards from occurring. So the data hazard, I'll show you, this is a reservation table. We show them like this. So in cycles, what you can see is which resources that are being used simultaneously. Okay, so there's 5 instructions, A to E, and this shows you what can be done at any one time. Now, here, in this particular architecture, we're allowed to read 2 registers at once. Okay, so you can see this instruction A can read 2 registers. If you look back at the picture here, it's set up so that they can read 2 at once. And propagating down the pipeline, right, that's how the pipeline would operate, right? Just like I showed before, just after the dishwashing example. But we have a problem. Here's the problem. It should pop up. Oh, it didn't pop up. The problem is that down in cycle 5, that instruction A, whatever it is actually finally writing its output value somewhere, be it to memory or something like that. Or no, register bank in this case, it's having the feedback. So it's actually using the register bank. Operation A in cycle 5 is finally writing something into the register bank after it's done its crunching of stuff. But way back in cycle 3, so back in time, B, operation B or instruction B has actually read the register bank. Now that may not be a problem. Okay, this is a setup where the registers are allowed to be written and read at the same time, provided it's not the same register. Okay, you can read a couple and write into another one. That's okay. But if it's the same one, you've got a big problem. You've got a poor computer software hacker that's written some code, and the result from A is not available for instruction B yet. So you've got 2 operations you've written, and B can't use the result of A because it's not ready yet. So it's not what you think it is. Ooh, okay, so there's a problem there, and that's called a data hazard. The data's actually not ready before you request it. And you think, computer scientists think that because an instruction comes after another, the previous one must have finished so you can get the value with the next instruction. It's a pain. So how do you stop that? You use what's called an explicit pipeline approach. This is a pain, explicit pipeline. Basically, you need to know about the architecture you're writing the code for and know the restriction on what can be done. Or you have a very smart compiler, which when it compiles your program, knows when things are interfering with each other in the pipeline. And what happens is it inserts no-op operations into the code. So you might have some beautiful code. It's really tight. It's the best you can write. And you go and put in a compiler. And the compiler says, hey, you're writing instruction A to the register file, but you're trying to read it back 2 cycles ago. Okay, what do? I'm just going to insert some no-ops in there. What do no-ops do? No-ops don't change anything. It's just an idle cycle or so of the CPU. So what that essentially does is, you can imagine this now, if B was a no-op operation, right, does nothing. C was a no-op, right, you basically let this bubble of no-ops progress through the pipeline. It's wasteful, but what can you do? Can't do anything. But it's very simple. Insert no-ops. A hardware way of doing it, so that's the programmer being aware of it and inserting no-ops, or a compiler doing it. But a hardware way of doing it, super smart hardware. The hardware recognises that it's going to have a data hazard. So what it does is it delays the execution of that second instruction until A has completed its write back, so it can read that value. So it looks very similar. So this actually looks very similar to the explicit pipeline, where these would be no operations here. But here, it's a hardware-based interlock. It locks B from running. Doesn't even fetch it. Okay, until A is finally written to the register. While it's doing that, you can be fetching B. So the next cycle, when you read B, it's already settled. Okay, so interlocks are a way of dealing with these pipeline data hazards. But once again, there's a problem. Dealing with it this way gives difficulty in the timing. Okay? So when hardware is inserting these pipeline bubbles, that makes repeatability and stuff a little bit awkward, right? Because you may simulate something perfectly on a computer, but you go and do it, and the hardware is making changes to how things are running. It might make the predictability of running the code more difficult, right? In order to get timing right and things like that. I'll say something about timing. Timing on general purpose computers, no one cares about. Okay? No one cares about timing, right? As long as the task gets done, it doesn't sort of matter which order things happen or whatever, but as long as the outcome is done in a particular time. With embedded systems, you may have to do particular things at particular times and be very strict on the timing. That's why we don't have all these fancy operating systems and stuff in embedded systems, right? Because we can't handle extra crap going on that could delay things. Okay, what about a control hazard? That's also a problem. So we've got data access problems in the pipeline, but we've also got control problems, and this is the cool one. Okay, let's consider A is now an instruction that says branch. It's a branch instruction. So we fetch it, we decode it, pull it from the memory, do the register bank read, put it through the ALU and everything. But if A is a conditional branch instruction, then we actually have to reach the memory write stage, so down here, at least here, maybe even the next one, before we know what needs to be loaded in the program counter. So the simple explanation is, if we've got a sequence of code, A, B, C, D, E, we're executing A and we're stacking up in the pipeline B, C, D, E, and finally when A has executed, it says go to X, instruction X. We've already filled the pipeline full of instructions that do not get executed now. So we've filled the pipeline full of stuff that it's not going to happen. Okay? And this is a control hazard, basically. So it fills up stuff with the pipeline with stuff that shouldn't be executed. Oh, how do we deal with that? Well, we can do some really clever stuff. A delayed branch. So we document the fact that the branch will be taken. Some cycles after the branch instruction has been encountered, so read, right? You've read it, oh, it's a branch. Okay, well, a branch may happen in 5 or 4 cycles in the pipeline. And once again, leaves it up to the programmer. This is stuff that we normally don't have to consider in general purpose computing, but for embedded systems where timing is crucial, ensure that the instructions follow the conditional branch instruction are either harmless, like no ops. Okay, so in other words, those instructions, so if this is a branch, you cannot have these instructions being destructive operations, messing around with the register file, overriding values. Because if you then go and branch to instruction X, which needs those values, you've gone and destroyed them with instructions that should not have run. Ugh, it's a pain. So what do? You basically do what's called a delayed branch. So you either do stuff that doesn't upset the state of the system, so you start padding other instructions in there, or you put good old no ops in there again. This is my favourite, speculative execution. So it's almost like what browser search engines do now, right? They kind of cache, some of the top hits that you get from Google, for instance, so because it's going to guess that you're probably going to pick one of the top 5 or whatever, so it's going to load them in the background anyway. And so that's essentially what speculative execution does here. It kind of estimates the hardware. As this code is running, it kind of says, well, I think that the branch is actually going to go this way rather than that way, so I am actually going to start filling up the pipeline with those instructions, X, Y, and Z. Right? We'll go A, whoa, I think that it's not going to be B, C, D. I'm going to start loading X, Y, and Z and do that. Downside is, if you're wrong, if you speculate, you're guessing. If you're wrong, you have to undo any of the changes that happened with those subsequent instructions. So you go backwards with that. So that's also a technique we use in embedded systems to deal with pipeline problems. But the problem is, except for those no operations and the delayed branches, which can be no ops as well, all of these techniques introduce variability in the timing and execution. So while they may be fancy and work well, it's very hard to predict the behaviour of the system under these conditions, particularly if we start getting multi-core, multi-threaded, interrupts with speculative execution. It's very difficult to work out the timing of events, right? How long will the processor take to execute those sequence of instructions? Who knows? Because it's speculating on which way it goes, and then it has to backtrack that. Very difficult to track, but it gives you speed. So it's not, not easy to predict what's going to happen with those things. Okay, so what's another way of improving the speed of a system or resource usage of a system? So pipeline is huge. Every processor will use it now, and you've got to be aware of that the architecture in the pipeline. Concurrency is another thing. So a program on a computer, we call it concurrent if different parts of the program conceptually execute simultaneously. A lot of concurrency is really just in our minds. On a single core processor, if it rapidly switches between tasks, refreshing the clock down the bottom, redrawing the mouse pointer as you move it, updating something else in the background, but it's doing those sequentially, very quickly, flipping between them. It looks like it's happening all at the same time. So that's what a conceptual concurrency is. It just looks like it, okay? But it's really parallel if you have separate functional units, so distinct hardware, multi-core machines, where the CPUs can actually operate independently. You can get parallelism. Or servers in a server farm, or distinct microprocessors on the one board, which we used to have. Under some of the old Pentium architectures, you could get motherboards with 2 CPUs that actually slotted in on the motherboard. Okay, so they were physically separate CPUs that did parallelism. So there's two ways you can do this, parallelism. You can do it as a multi-core architecture, and we're kind of used to, if we're speaking Intel, you know, the core lot of processors, Core i5, i7, quad-core, hex-core, all that sort of stuff. Easy. You've just got multiple CPUs. So you can do stuff in parallel. For typical embedded systems, we generally don't have multi-core processors because we want to have things repeatable and have things fairly tight in terms of the timing. So we do other things like what's called instruction level parallelism. So CISC instructions, subword parallelism, superscalar, and very long instruction word. And these are techniques that are used in programming to get around the concept of concurrency. All right, I'm going to talk about CISC briefly, and then I think we'll talk a bit more about subword and VLIW architectures maybe in the next lecture. We'll keep it going. So what's CISC? RISC and CISC. CISC, complex instruction set computer. These are processors that have very specialized instruction sets in them. Okay? I'll give you an example. There used to be more of them around, but in terms of general purpose computers. But these days it's normally DSPs that are very specialized in terms of the operations that they do. So for instance, a general purpose computer with a reduced instruction set, RISC, RISC, will have pretty dumb instructions. Move value from register to here, add some things, good. Very basic level stuff. A CISC system will have complex instructions like instantiate an FIR, do Viterbi decoding, implement a Kalman filter, right? These are very specific instructions that have a lot of structure underneath them, not just add a couple of things and move it there, okay? So they have, as I said, complex instruction sets. But it's very difficult for a compiler to optimize instruction sets that are complex. Very difficult, because you can't get down to the low-level stuff, right, of like adding and shifting stuff. You're still dealing with very complex tasks in the one instruction. And so typically, if you ever learn to program DSPs, you're going to love it, because you typically use code libraries that are written at very low level. They're written in assembly language.